All right. I think it's probably everyone that's going to be here for now. I'm going to go ahead and start. So, thank you all for coming. Today, I'm going to be giving the presentation on just going over, I guess, creating a covert communication in an ICS environment. Full disclaimer, I have been reading some white papers within like the last couple months or so, and a few of them do go over different types of covert communications. One kind of caught my eye because I thought it was kind of cool. I haven't used Modbus as much prior to, I guess, this last year or so, and so getting into it and actually trying to like mess with the protocol a little is kind of cool. And I saw this paper and thought it was kind of a neat thing, and that's kind of where a lot of this PowerPoint spaces comes from. So I'm just going to give credit where credit's due. So covert communications as a concept is fairly old. I mean, this is something that people have been doing for a very long time. I personally just find them really cool, and basic things like encryption are kind of lame. I mean, they're still cool too, in their own right, but covert communications are neat, especially something that's ICS related. And even if it's not ICS related, the concepts that we're going to talk about today can be moved and translated to other, I guess, other regimes. Like you could say, let's implement this in a normal IT or information technology network. So first I want to talk about what is an industrial control system environment, or what is an ICS environment. Well, ICS as a term is kind of general. It refers to the control systems within an industrial environment. I know that's kind of like using the name against itself, but these are like, if I have a giant hydroelectric dam, this is normally going to be what is controlling that dam. And a lot of times those systems are kind of just basic. They can be anywhere from like just switches to maybe being as advanced as a computer that has full output control to this giant system. Can control lights. Maybe it's like a Raspberry Pi you can even consider could be a ICS or some sort of industrial controller, because you could hook up the GPIO pins to a relay, and that relay turns on this giant machine. Like the extensibility of this is really just to refer to systems that are inside these environments that do control things. And you might, that things part is kind of related to Internet of Things. That's kind of where I'm going to be alluding to here as we go along. Another way you might refer to some of this technology might be operational technology, or OT. So you might hear terms like IoT or OT kind of interchange within ICS security. Really what it comes down to is just those controlling mechanisms. So I'm going to explain a scenario here. We have a dam, and one of those controlling systems is we got this relay here. This relay is a good old SEL 700GW. If you're not familiar with it, that's okay. It's a wind generator relay, and this can do some controlling of just different devices that are contained in wind generation, or I guess wind generators, I should say. Someone along the way decided it would be cool to network these, and that's nice. Being able to communicate over a network so that you can kind of remotely control them, but exposing them to networks becomes a problem, because now when you have technology that's being implemented into these, like slapping an Alexa to this, where it becomes smarter and smarter, these systems tend to have greater capabilities, which add to a larger attack surface. So that's kind of what we're going to be, I guess, dealing with security-wise. So whenever we refer to ICS relating to cybersecurity, it's dealing with these systems just being super smart, or at least having capability that's not just a dumb switch. So they speak Ethernet, they speak Telnet, SSH, whatever it is, and you're able to control it from usually another office. So if you might have seen certain videos online, like say by Tom Scott, who does different exploratory ventures into dams. That's not his only thing, but that was one of his recent videos. He was discussing how a lot of times those dams, there's like no one there. And that's usually because they're managed remotely. Software that's made by these manufacturers gives us that capability to. But despite it being specific software by that manufacturer, they still speak protocols that we see day in, day out, such as Telnet, FTP, SSH. So really what it comes down to is like these networks are really just kind of quirkier IT networks. So maybe they don't always speak, you know, these SSH protocols, but a lot of times they will. And even crazier is sometimes you'll see Windows environments in those environments. I know it's redundant. A lot of times those human management interfaces that allow us as people to kind of use a GUI to control these environments requires some sort of GUI interface to use, or some sort of not terminal based interface, and normally that's going to be from a Windows system or on a Windows system. And a lot of times they might find themselves in those environments, and so it kind of adds more complexity, a bigger attack surface, yada yada. You know, the convergence is really what I'm trying to allude to here, where while this was initially just one basic system, now we got Windows environments too. So again, those protocols that we're looking at, very similar. We might see some unique ones though, such as Modbus TCP, DNP3, BACnet, EtherCAT. Maybe you probably haven't used that on your computer at home, but these are normally protocols that are specific to ICS and OT environments. So let's talk then now on what we mean by covert communications. So for those of you that aren't familiar, covert communications are really just a non-standard way of communicating. The opposite would be overt communication. So us maybe using like Telnet, which is pretty overt, or even like a netcat socket connection. We're trying to communicate over some wire and send a text chat, and anybody that's snooping on it and listening can actually kind of just see what's going on there. The covert part for covert communication is to refer to a type of communication where it's not exactly obvious that a communication is going across there. This is, I guess, you could compare. It's like I think I've heard an argument where like encryption could be a covert communication, but the problem with that I see is that you still know that there's something going across it. Like there's obviously something there, but I'm talking more like the ones that are, say, hiding data in ICMP headers, because ICMP, or maybe like you might refer to this as a ping echo request or echo response, has it has data segments within its defined header for that protocol, but there is unused space that it doesn't need. So you could hide data in there. Or my favorite one, which is actually sending DNS requests at different times, and then based on how long you take between each request, you can define a 0 or a 1, and that is a type of communication protocol. It's probably a very low bandwidth as far as how much data you can get across at a given time, but you still are able to get discernible information at the other side. And when you just look across the wire, it's not inherently obvious. It just looks like a bunch of DNS requests. And if to the untrained eye, and probably to most people, even IDS systems and automated systems, it's a little hard to kind of discern like, oh, well, that's probably malicious. Of course, pattern analysis and long-term analysis over these types of data transfers sometimes can pick that up. But the idea here, it just doesn't look like a communication. So the problem here is kind of like what I was kind of just going over. We want to be able to send the data without it being obvious. A lot of times you might try to go for non-conventional things in nature. And one of the main things I want to keep in mind here is that we have a sender and we do have a receiver. So you might more or less relate this to like the people in China that are trying to get information out to people that aren't in China. Sometimes that gets, censored. So it gets censored, and they want to be able to still get that censored data out or censored data in. So you might try to use a communication line that doesn't necessarily look like it's being communicated across the wire. So techniques such as like maybe domain fronting to try to thwart automated detection or people just peering in to see that communication occurred. That's kind of the idea that we're trying to keep here. I want to get a communication out to somewhere. And it's going to be from some sender to some receiver, and both of them are going to understand this protocol and understand how it works, and they're going to be able to decode it in some way. I'm going to keep mine not bidirectional, but you could totally implement something that is bidirectional. It just becomes a little bit more complex of just how to get the data back the other direction. So let's start making the covert comm. So first you got to choose a protocol. Like we've discussed so far, there are a lot of different protocols. I'm just going to choose Modbus because, again, it's common, I guess, in ICS environments among DNP3, but it also is something that like I said, a little bit more familiar with. specifically Modbus TCP. There's a different version of Modbus, but it's not relevant for what I'm going to be doing. So let's find some abuse opportunities. Like I was saying before, in protocols such as like the ICMP header, there's going to be things that are a little weird about how the protocol gets structured. So for ICMP, it's that extra data segments. For Modbus, there's not a lot of description of how that packet, I guess, is structured. This link shows it. It shows, if I want to send a command, here's how it looks, but it's not necessarily a segmentation like you would see in an ICMP packet. It's just literally, all right, well, we took TCP and then within that we just stick like 20 bytes, but they do have each a meaning, and we'll explain that here in a second. But that's it. I'm trying to just more say it's less structured. It's just literally just a byte string. That's really what you're looking at for Modbus. And normally the format for that byte string is like some segment that's referring to the command, another one the address, account, maybe a unit size. So it's not super complex in what you can do to, I guess, spoof it. Since the command is talking, you're using this protocol to communicate with another system. If you get any part of that wrong, there's more than likely going to be an error that gets sent back. And actually this Modbus documentation here does discuss some error responses and how that, I guess, looks when it does respond incorrectly. So that is something to keep in mind, I guess, is when you're making a protocol, you don't want it to stick out like a sore thumb. Another thing to keep in mind is keep it simple. I don't want to necessarily deal with modifying headers because that sounds like a pain. So what I'm going to do is try to see if I can hijack something of just the general use of this protocol. There's a lot of different normal functionalities that this protocol offers, as with other protocols. And, maybe I can make use of that. And it would probably take a lot less time to mess with that than it would be to, add extra things into headers, find what doesn't get hit on certain versions of this protocol, or what does get detected by certain versions of this protocol as an error because maybe it was implemented correctly. So, there's a lot of different things to think about when you start futzing with that. But with this, I don't have to implement anything too crazy, and I can kind of just use it as is. So any basic client should technically be able to communicate across the wire without any heavy modification. So let's look at the different functions that are here. Looking at the functions for Modbus, we got read coils, write coil, which actually should be write coils, I believe. No, it's write coil because it's a discrete value. We got read register, write multiple coils, read multiple registers, and write multiple registers. That's a lot of functions. It's not, I guess a ton. I guess you could have more, but kind of just skipping over hand wavy magic. More of the common ones that you'll see are read coils, write coil, and write multiple coils. And the reason for this is because a lot of times when someone's using this type of system that speaks Modbus, you're probably going to be reading a status of a coil. So if a coil, which actually I should explain this here, a coil is usually a discrete value of 0 or 1. A register can be any 2-byte integer. This is important because this will also explain why these are commonly used. Coils, since it's a discrete value, kind of can represent on or off, whereas a register is probably going to be more of like a value of, say, like a phase angle of a generator, or maybe the voltage level of some device it's connected to. So it's less discrete as 0 or 1, but more like I can set a floating point value there and set what it's going to tell another device to be. The reading of the coils and the writing of a coil means that I'm probably going to be checking to see if, first off, for the read coils, is a switch on or off? Is a system on or off? Or if it is on or it is off, I'm probably going to write coil or write multiple coils to turn these things on. So I'm going to probably change that state. So maybe it's 0, I'm going to change it to 1. Maybe it's on, I'm going to turn it off. So that's usually why these are the mostly used a lot. A lot of times registers that hold those values for things such as voltage and phase angle don't get changed a lot unless they're being read from. You might see read register happen, but it's not going to be as frequent. So looking at how these requests look, they're not too complicated. They're actually really simple. So again, they got 3 sections for this byte string that you'll see, and they yeah, I mean, there's nothing too crazy about it. It's pretty dead simple. So let's test some implementations of those different commands. Some things we'll notice is that the write command specifically, the write coil, I should say, and write multiple coils are an actual, it's an action that's going to modify something, right? So we're writing to a location, and that could cause problems. So if it's, like, say, writing to turn off a generator, well, that's going to be pretty obvious that I'm turning off the generator. I guess an option that you could do is check what the state is first by doing a read coil and then do a write coil to just write it to that same state. But then you risk the fact that maybe somebody changed the state while you were trying to write, and this goes downhill. So it's probably not good to do. So write coil and write multiple coils are out, which kind of just leaves us with read coils. What's kind of nice with read coils, though, is that we can kind of just read. So actually, let me define what the read coil specifically does. We have a function code and address, so it's some offset we're going to read from, and we're going to read a quantity of coils. Oops. So we can read from an address and then read X amount of coils. That's kind of just as much as we want. We don't have to have a limit on that. We just can't read 0 coils. So what's nice about this is normally you'll see that a read coil operation is normally just trying to read one singular coil, and the implementation actually allows you to do more than one coil, but the response from any Modbus slave will always say, here's the value of this one coil. So you could say, I want to read at address 1 the value of 3 coils, and it'll still just give you back the 1 coil, which is a really weird, I guess, just a Modbus-ism, just in the implementation of the protocol, and usually requires some extra overhead or additional modifications on the PLC or whatever device is using Modbus. And understanding that weird quirk actually will allow us to do some cool things with being able to encode letters to maybe different style or different read coil commands and different combinations. I'll go over that in a second. So let's do read coils, because we can't do read register because, again, not common. So we're really just stuck with the one read command. Thank you for sitting through that long explanation of weird Modbus things. I want to go over some assumptions first. We have assumed that we've already compromised the target environment. We also can compromise a Modbus server, also maybe referred to as a Modbus slave. The difference between a slave and a master is that a slave can't initiate connections, but a master can initiate connections. It can start the connection with the slave and get values from the slave, tell it to do certain actions, but a slave will never be able to reach out to the master or any other system, normally. The Modbus slave has an unlimited number of coils. These are going to be usually limited by the type of device or what types of things are connected to it. So that limitation is usually a physical limitation. For this case, I'm going to be using all simulated devices, so this is technically unlimited. The target network has no IDS in place, pretty obvious. We know how to baseline the network traffic. I'm just going to hand wave that. We'll explain that later. We have discovered that the Modbus slave is dual home, so it has 2 network interface cards, and I'll come back to that later, of course, as well. So our scenario is our master 1, our Modbus master, is going to be able to make an encoded communication and send it to the compromised slave 1. This compromised slave is something that we had infected at some point and modified the firmware potentially, and we were able to inject in some additional code. The Trojanized code basically in this slave will read the command and strip off any special version of the read coils command. So this would be whatever we're considering our encoded command. And then it's going to send that special version that it stripped off and whatever values from that and send it off to the master 2. So in this covert communication, keep in mind, master 1 is our sender and master 2 is our receiver. For this encoded part, we will need to be able to multiplex and demultiplex ASCII bytes into a read coil command, and I'll go over that code in just a moment, so just keep that in mind. Let's first, I'm going to also show the network diagram that we're dealing with. Nothing too complex. It's like really flat, so nothing too crazy going on here. I have a Modbus master 1 who's technically inside of the network, or at least at some I guess it's not going to be on the same network as the slave, but it's assumed that this is the target network. And then he's able to send out to the compromised slave some encoded message through read commands, and the slave is going to send those out somehow to the master 2, and the master 2 is going to somehow be able to decode it. So let's talk about that translation layer. We can convert ASCII to read coils commands. This is pretty easy with the ability to have unlimited numbers of coils. If we had limited numbers of coils, we would have to reduce probably what our pool of data that we could send, which means that we would have to play around with maybe compression, or like what letters could we leave off to get a proper encoded message still across, and so on. But since we don't have that limitation, we can make use here and have, for whatever character, pair that up with an address that we want to read from, and a count that we want to count, or I guess the amount that we want to count and read from. So the thing to keep in mind, I guess, with this too, so if we recall what I was saying before, a read coil command you'll most commonly see is reading a 1, either really just reading a count of 1. So it wants to read 1 register. So whatever address it is, it could be 0 to 255. There's a maximum, I forget what it is off the top of my head, but you'll probably just be reading the 1 out of that, which means that that'll be our baseline. This is known as normal behavior, and I'm going to say any deviation from that is probably a special, one of our special encoded commands. So that'll be anything that's 2 and greater. So then we'll keep that and say, all right, well, we can make that translation layer and say 0 is actually now going to be a read command where we send 0 and a count of 2. 1 is going to be 0 and a count of 3. So whenever that gets stripped off and the other Modbus master receives this, it's going to go, hey, 0, 3, that's a 1, and be able to build our message down on the other side. Then all we need to do is, once we have this cipher or encoding, we can use a Python library such as PyModbus and create a client that can send read coils commands to the remote server. And actually the code in here is a little wrong, but it doesn't matter, and I'll explain that later if someone asks, but it's right for the operations here. So that's encoding it, sending it, and that's it. That's all this person does, is he's just sending it. Remember, we're not doing a bidirectional communication, so we don't have to worry about trying to receive something here yet. But the listener does need to listen. So what he's going to do is he's going to receive the content, and he's going to run it through the cipher for every byte of, every basically byte of data that he gets from the compromised slave, and decode it, and then build up a message. And every message that gets sent is going to be new line terminated. And once it becomes new line terminated, then the other receiver will know that this is an ended message, and then just print out the message to the screen. It's going to be simple. I'm not going to do anything super fancy. I'm not going to send a whole zip file over the wire, because I feel like that will cause that it'll have errors. This is not a robust protocol that we're dealing with here. So the interaction, like I was saying before, and I'm going to lay it out here with now our new translation scheme, kind of what it looks like on the wire. So the Modbus Master 1 is going to say, hey, Modbus Slave, I want to read coil 1-1. And since that's just like a normal interaction, the target's the compromised slave is going to say, okay, here's the value of that register. Well, the other interaction would be when we say 0-2. And, well, the slave is going to go, okay, well, I'll send you back this, and we don't really care about what the value is there. It's going to be some value of its choosing, and more than likely it's going to be the value at address 0, and it's going to give you, of course, 1 value back. But then it's also going to strip it off and say, all right, hey, Modbus Master 2 or receiver over there, here's just 0-2. And the receiver is going to go, ah, cool, and be able to translate 0-2 to B. That's pretty trivial. It's kind of nice. So let's do a demo and hope that works. Let me change screens on both the Discord and OBS. And I should have everything pretty much set up. So does anyone have any questions in the meantime? Or is everyone going pretty good right now? All right. Cool. So change screens there. All right. So what I have here is I have a system that's set up very similarly to that diagram that I explained. We have a Docker Compose environment that's built up, and we have our attacking machine here. Even though both this says attacker and this attacker, this is actually the target machine. So this is going to be our compromised slave, and this is going to be just the basic Modbus Master 1. We're going to have a Modbus Master 2 over here, which is the receiver, and I guess for all intents and purposes, the code change that I was talking about earlier for the Modbus Master 1 is that you don't want to send 0 for the count. It'll result in error. So you want to send a count of 1 at least, just to make sure that it's clean. What I'm doing here is I added an extra little thing to kind of obscure how that traffic looks across the wire. So when someone's looking at this in, say, PCAP format, it's kind of jumbled where we'll see, all right, so for some address, we'll send the value that we want to, all right, like encoded value. And then for that same address, I'm just going to send 1. So it makes it a little bit more broken up. But since we still understand that the remote system will still get that extra counted value, so this is going to be greater than 1, then we'll always get this value instead on the receiver side. And you'll see that it cleanly decodes on the other side. I know that's probably a little confusing, and I apologize. Python 3, master 1. And I'm going to start up my compromised server. Now, the adversarial slave is not the interesting part. What is interesting is this part. Let me go here. So this is the modification. If I, okay. And then it's this guy. There we go. So the modification that I made is this code right here. So I put it in the decode request. So in PyModbus specifically, and of course the implementation for this is going to be different depending on what system you're attacking. So if I'm trying to make a Trojanized system firmware, this is going to be different, of course. Just keep that in mind. But for PyModbus, if I had, for whatever reason, a PLC that was running PyModbus, this would be some implementation I could use. What's going on here is I'm just checking to see whenever a decoded command comes across, and specifically this decode command is for when read coil happens, then the decode request, the decode function is going to check and see if that count is greater than 1. If it is greater than 1, then we're going to go ahead and make a socket connection and then close out the socket connection while sending the address and the count to our remote or receiver. It's just going to siphon it off, send it in another direction. So this is kind of nice because, super simple. Just the address and then the value. And we'll be able to decode on the other end. And then, yeah, nothing crazy else happens here. We're not actually modifying any control flow. It's a little, obviously control flow, but we're not changing this in any drastic way that this server is going to be broken in any sense. So it's going to be, pretty stable. So scripts here. And of course I didn't include any fancy logging or output, so I apologize. Actually this will log. So I'm going to set up my master 2. So this is going to be the person that's receiving the data. And we're going to send a super spooky message. And what we'll see here is this is our encoded array. This is what gets translated. So capital S got translated into 56, U 32, P 27, and so on. On the Modbus side, on the server, we'll notice that there was a lot of traffic sent. It's a little weird, I think, to read at first, but I'll help you decode it. So we see the client connected here, and it got some data. This is going to be whatever command, and we can see that it decoded it to a read coils request. Then it started another connection that's going to be another read coils request, and it's just doing this over and over again. And it handles it and processes it and sends back a response correctly. There's no errors here. The server's having a grand old time. The address and count's a little weird. I think this is just more PyModbus not knowing how to represent data. But the value across the wire, it kind of gets represented a little weird despite saying, okay, well, this is probably going to be say 4.5 or 10.6 or whatever. It might say still 10.1. And this comes back to that behavior that we were talking about, where even though that we might have requested a count greater than 1, it's still going to send back a count of 1, just regardless. And this is just more of a protocol implementation. And then here, we got an uber spooky message, not super spooky message. So that's a little unfortunate, but it's usually because the initial connection is a little weird. It has to make that connection across first, and there's some like idiosyncrasies that happen. And this is just more to go towards the fact that it's not a robust protocol in any sense, but I still was able to get a general message across. And the more I'm saying, I'm like talk, and so I'll send that across, and talk is probably going to drop the initial T. But then if I send another command again, it actually missed a letter. Well, let's send that again while we still kind of have an active session going. Then we see that the full message got sent. So that's just more of a weird ism that occurs during, I guess, this implementation of this covert communication. Okay, I'm going to switch back then to the PowerPoint. Let me also change OBS. That's the wrong monitor. There we go. All right. So the traffic here is normally what we would see in a normal Modbus communication. This is 26 26 packets that we see going across. And we can see that there's no errors there. Modbus Recoil command comes across, the response gets sent, everything's hunky-dory. At the communication that we just created, we can see that it actually generated up to 313 packets sent across the wire. Again, still no errors, but there were multiple read coils requests that happened consistently, multiple connections that were created over a specific time. A lot of times when say you have a Modbus client connected to the server, it's usually a consistent TCP connection. So this made a connection every single time that it tried to send something. So that might be a poor thing on the library part. And so I wasn't emulating correct traffic well enough, or at least how a client normally would act. So this might look a little funky. But I guess the main point I'm trying to get aside from that's a lot of packets. That's a lot of data going across. That's really loud. 26 packets versus 313. If I'm just flooding the network with a bunch of read coils requests, that's going to be a big problem. So just something to keep in mind with some of these protocols, because if you're not discreet, it's going to be kind of obvious that something weird is happening. So some of those issues really are kind of what I just talked about, but some other ones would be, this protocol is still kind of susceptible to junk. By that I mean, say you have Billy, who is horrible at using Modbus and decides that he wants to read from address 20, he wants to read 300 for some reason. He wants to read a count of 300. So while that count is greater than 1, it's not one of my messages. But my adversarial server is still going to try to decode it because it was greater than 1, and it's going to fail to. It's going to be it may fail to if it's inside the cipher. If it can't decode it, it'll probably crash or do something funky if it's not robust enough. But yeah, there's junk that could be included in my message. But I think the good news is there's still no TCP errors or Modbus errors, so that's honestly a plus in my book because I was still able to get something across that was somewhat legible. So let's go over those assumptions I made earlier. First one, we have already compromised the target environment. I think this kind of goes without saying. You really can't do much without compromising maybe an environment, especially when it comes to trying to do a covert communication from inside of a network. But this kind of idea can still, like I said before, translate without even needing to compromise a network. If this is a covert communication in just a normal environment that maybe you have access to, you didn't need to do any compromising. You were technically already part of the network anyway. So that's, it's never always about compromising that environment. As for Modbus servers, sometimes they're maybe even just on the internet because that's an unfortunate thing that occurs sometimes. So the Modbus slave has an unlimited number of coils to use. Kind of like what I was saying before. It's really just based on the PLC or whatever device it is. It may not have an unlimited amount of coils, and it might error back at you if it doesn't have enough to suffice the request that you're making. So that can also not only limit what we're doing as far as communication wise, but can also add to some extra red flags on the wire. And then kind of one of the blaring ones, the target has no IDS. Well, that's not reasonable. OT networks and IT networks nowadays pretty much all have some sort of intrusion detection system or anomaly detection environment and some sort of way to be able to detect when issues are going on in an environment. So really what happens with this is we just need to worry more about OPSEC and try to make something that's a little bit more robust and a little bit more quieter. I think this protocol of just communication right now is a little funky because while if I was to break up the communication just ever so slightly, that would lay room to more errors being introduced into that whatever communication happens versus me flooding the network. I can kind of get all the packets right away as quick as I need them. So, there's trade-offs to that. I would probably get detected less if I just spread it out over maybe the course of like an hour. But of course, you wouldn't want to sit here an hour and wait for me to get a message. There's going to be probably a little bit of an interesting thing with how the slave is talking. Like, why is the slave making communications to the outside network? That's a little weird, especially since we discussed before. Modbus slaves aren't supposed to be making connections to the outside world. So why is it? And this kind of goes into the idea of it's not dual homed. Normally, you'll see this not being a thing. Sometimes you will. Sometimes there are ICS systems that are dual homed, but a lot of times it's usually just one network interface card that you're dealing with, and that means that whatever data is going to it, the response is going to go across that wire, even if it's to another host in another network. So that kind of lays more lanes for an IDS to be able to detect what is going on that wire. We also know the baseline for the traffic. This is a little bit more interesting because if you have compromised the network and you understand how the network is looking like maybe you somehow had access to a spam port, that's pretty trivial. But we don't always have access to just random spam ports to just listen to flooded traffic and just see what the network looks like. So this tends to be a little bit more interesting to try to figure out. Sometimes attacking devices such as like intrusion detection systems or firewalls will give access to this kind of ability. Like we can then start to see, okay, what does the network look like? And if we have access to change maybe how a computer, like if you have maybe pseudo permissions on a computer in the network that has the ability to turn into promiscuous mode, maybe you might be able to even see what is on that wire there. So there's a few other additional steps to go there. So I did kind of like wave over that, but baselines really help with trying to make sure that your behavior matches what's going on, and especially with anomaly detection, with doing some sort of behavior analysis on the traffic. This is extra, like, you should try to at least do this because you'll stick out like a sore thumb pretty quickly. And then just kind of going back to that, Nick, really just it's something that we'll have to try to then translate into maybe a more robust communication protocol. We just want to make sure that any of the traffic that's going across, we just need to make sure it doesn't look suspicious and maybe try to find an additional way to send or another additional layer to be able to actually get that second message out to our receiver that needs to be able to receive it. But of course, I didn't want to implement that here. Thank you for coming to my TED Talk. And if you guys have any questions, feel free to reach out to me here or talk to me here. But that is the end of my presentation, and I appreciate you guys taking the time to be here for about 30 minutes-ish. Does anyone have any questions? All right. Class dismissed if you want to go. Don't feel like you need to be here.
Thank you, Nathan.
Yeah. Thank you guys for coming and watching.
I have a quick just thought. I don't know if I'm sure you thought of it already, but in working or making your Python scripts, did you try doing any rate limiting just to see if it changed the like just some of the errors you got, or did you try adding any like sequencing, like, or just having like a kind of ordered system for your encoded packets? not at the packet level, obviously, but like just like, per character basis, like maybe like ordering them so that it came in the right order on the other side.
No, I didn't. I was purely going based off of what. So when the slave tries to strip off the values out of that read coils command, it was just sending it right away, and I was just taking the connection as it got it basically, and just building the message from there. I was using a threaded server, so each connection that would come out, it would make the connection, send it, and then my threaded server would receive it, add it to a string, and just keep going. So if it received it out of order, it would just be out of order. I didn't have any any CRC or any type of ID for that sending. That is something I could add though, and you could definitely you prepend or append an ID of some sort or some way to parse that, and so you can be like, okay, well this is 1, this is 3, well I need to wait for 2, and just manage that way, or some other method of trying to tokenize that. But yeah, no, I didn't do that. That probably would be a way to also make it more robust so that you do get a more complete message on the other side. And if you notice that maybe a data that gets to you is not parsable in that sense, that you know that it's junk data, and so you can throw that out, which also would make your protocol probably a lot cleaner. So that is a good idea. It's just not something I did.
Oh, thank you for the talk.
Yeah, of course. Thank you guys for coming. It was fun. This is something that like I said, I've been kind of just reading through some white papers the past few months, and this is actually funnily enough it was a challenge for the Cyberforce competition. I made a PCAP and gave everyone that to try to figure out the protocol across the wire, basically. Of course, I wasn't just leaving them out to dry because I feel like that'd be kind of asinine if you're just given a bunch of read coils requests and then you have to figure out what this crazy encoding is that I did. Even though it's not like super crazy, but just looking at it, you won't be able to figure that out necessarily. So made it a little easy and just threw in somewhere in there one of the sender scripts, so they had the encryption, or not the encryption, but the encoding. And actually, I can show. Me also kill my recording, but so